Welcome to this lecture. In this lecture, we will continue our study from the previous lecture. In previous lecture, we have discussed the method to find out fundamental matrix solution. In fact, we have defined what is fundamental matrix solution, and we have seen certain properties of fundamental solution. For example, if you have n linearly independent solution of x dash equal to Ax, then you can form a matrix, and we can call that matrix as a fundamental matrix solution. And also we have shown that any matrix is said to be a fundamental matrix solution provided that x dash equal to, it satisfies this differential equation x dash equal to Ax, and determinant of that matrix is non-zero for all t in that particular interval. Then we call that matrix as a fundamental matrix solution, and based on that we have proved that e to power at is also a fundamental matrix solution. And also that we have shown that if we have two fundamental matrix solution xt and yt, then they are related by a non-singular matrix, and we can write one fundamental matrix as a like yt is equal to xt times constant matrix C, where C is a non-singular matrix. And now we start after that, and let us now we prove that let xt be a fundamental matrix solution of the differential equation x dash equal to Ax, then we can calculate e to power at equal to xt into x inverse 0. In fact, if you recall, while in the beginning when we start solving this problem x dash equal to Ax, then we have proved that e to power at is a solution of this, and corresponding to any vector e to power atv is a solution of this. So here the problem of finding e to power at is quite difficult, and we have obtained some alternative method to find out the solution, linearly independent solution of x dash equal to Ax. But now with the help of those n linearly independent solution, now we want to calculate this matrix e to power at, and so that e to power at into any vector of size n cross 1 will serve as a solution of x dash equal to Ax. So basically we are trying to find out e to power at with the help of n linearly independent solution of x dash equal to Ax. So now we say that once we have n linearly independent solution of x dash equal to Ax, then we can form a fundamental matrix solution, call this as xt. Then we say that e to power at we can calculate as xt into x inverse 0. So now let us prove this theorem, which is proved like this, that let xt be any fundamental solution of x dash equal to Ax, then using the previous lemma and the fact that e to power at is also a fundamental solution, that we have proved in the previous lecture. So we have shown that your xt is a fundamental matrix, and e to power at is also a fundamental matrix. So it means that I can write xt as e to power at into C, or I can write e to power at into e to power at equal to xt into C, where C is a non-singular matrix and we want to find out the value of this non-singular matrix. Now for this let us take t equal to 0 here, and when you take t equal to 0, then e to power at is reduced to I, and xt is reduced to x of 0 I into C. Now since x is a fundamental matrix, so determinant of x0 is non-zero, so it means that we can say that x0 is a invertible matrix. So multiplying by x0 inverse throughout the equation, we can say that your C is coming out to be x inverse 0. So we can say that once we have the value of x inverse 0, then we can write down the fundamental matrix e to power at in terms of xt as e to power at equal to xt into x inverse 0. So this looks very tiny result, but it is very powerful in the sense that from any fundamental matrix solution you can calculate e to power at by just writing xt into x inverse 0. Okay. And once e to power at is given to you, then you can take any constant vector of size n cross 1, and you can write down the solution of x dash Ax as e to power at into that vector v. Now let us take one example so that we can give the the illustration of this theorem 1. So, here in example 1 we need to find out e to power at where a is given as 1 1 1 0 3 2 0 0 5. Now, here we have taken a very simple example to discuss because it is an upper triangular matrix and eigenvalues you can easily calculate as 1, 3 and 5. So, here your lambda 1 is equal to 1, lambda 2 equal to 3 and lambda 3 equal to 5, and since we have distinct eigenvalues. So, eigenvector we can easily calculate, and we can calculate corresponding to 1 as 0 1 1 0 2 2 0 0 4, and you can write it a b c, and you can calculate that b plus c equal to 0 and c equal to 0. So, this implies that your b equal to 0 and c equal to 0. So, we can find out the eigenvector corresponding to lambda 1 equal to 1 say 1 0 0, you can calculate it like this. So, here we can say that to find out e to power and in this way we can proceed further. So, let us start with this solution procedure. So, to find e to power t a, we first find out a fundamental matrix solution of x dash equal to a x, and then we can use the result of previous theorem. And as we have pointed out that a is an upper triangular matrix, and hence eigenvalues of a are nothing but the diagonal entries, that is lambda 1 equal to 1, lambda 2 equal to 3 and lambda 3 equal to 5, that we have just pointed out. Now, since we have 3 distinct eigenvalues, so corresponding eigenvectors are also going to be linearly independent eigenvectors, and hence we have 3 linearly independent solution of the form e to power lambda t into v. So, for lambda 1 equal to 1, we have already obtained that 1 0 0 is an eigenvector. So, solution is given as x 1 t equal to e to power t into 1 0 0. Similarly, we can find out solution corresponding to lambda 2 equal to 3, lambda 2 equal to 3 and then lambda 3 equal to 5. So, and we can find out that it is nothing but 1 2 0. Let us calculate the eigenvector corresponding to 3. So, for that we simply say that a minus 3i will be what? A minus 3i v equal to 0. So, it is what? Minus 2 1 0 0 0 2 and 0 0 2 and a b c equal to 0. So, it means that here c is 0 and we can write minus 2a plus b equal to 0. So, b is equal to 2a, you can say. So, we can write down solution as, if a is 1, then b is 2. So, 1 2 0 is one eigenvector. So, it is written as 1 2 0. So, second solution corresponding to lambda 2 equal to 3 is given as e to power 3 t into 1 2 0. Similarly, for lambda 3 equal to 5, a minus say 5 I into v equal to 0 implies that here it is. So, it is, let me write it here, what is the matrix 1 1 1 0 3. So, here it is minus 4 1 1 0 and 3 minus 5, it is minus 2 2 0 0 0, here it is, and it is sum a b c equal to 0 0 0, and here we can simply say that it is what? It is b equal to c and minus 4a plus b plus c equal to 0, and in second you can get minus 2b plus 2c equal to 0. So, b equal to 0. So, minus 4a plus 2b equal to 0. So, b you can write it 2a. So, we can simply say that if we take a as 1, then it is 1 and then b is 2 and c is again 2. So, here we can say that corresponding to lambda 3 equal to 5, your eigenvectors is given as 1 2 2. So, x 3 t is given as e to power 5 t. So, now we can find out a fundamental matrix solution of x dash equal to a x as x t, as x 1 as first column, x 2 as second column and x 3 as third column. So, x 1 t is e to power t 0 0 and x 2 t is e to power 3 t 2 e to power 3 t 0 and x 3 t is e to power 5 t 2 e to power 5 t and 2 e to power 5 t. So, we have obtained one fundamental matrix solution of x dash equal to a x. Now, to find out e to power a t, we need to use the formula e to power a t as x t into x inverse 0. So, we need to calculate x inverse 0. So, x inverse 0, so let us find out what is x of 0. So, x of 0 is nothing but, so it is 1 0 0, say it is 1 2 0, it is 1 2 2, and we can find out the inverse using any of the method, whether it is say usual method or Gaussian elimination method. Any method you can apply and you can find out x inverse 0 as this. So, x1 inverse 0 is 1 minus half 0, 0 half minus half 0 0 half, and you can simply say that here x 0 has determinant non-zero. So, x 0 is invertible. So, x inverse 0 exists, and now we can calculate e to power a t as x t into x inverse 0, and which we can calculate is like this. So, here we can calculate e to power a t in a very concise manner once we know a fundamental matrix solution. Otherwise, calculating e to power a t for matrix A is quite difficult, because it is an infinite series, and summing up sum of infinite series is quite difficult. So, this infinite series is now converging to this matrix which is given here. So, in this way, this calculating e to power a t using one fundamental using a given fundamental matrix solution is quite useful. Okay. Now, there are several algorithms available to calculate e to power a t. In fact, more than 3 are available, but here I am just listing only one. So, and this method is known as Poisson method for calculating e to power a t, and the idea behind calculating e to power a t is the Cayley-Hamilton theorem. Cayley-Hamilton theorem says that it is basically Hamilton theorem says that every square matrix satisfies its characteristic polynomial. So, it means that characteristic polynomial is characteristic equation is a minus lambda I equal to 0, and it says that when you expand it, you will get a polynomial in terms of lambda, and by solving this only we are getting the characteristic roots. So, here Cayley-Hamilton theorem says that matrix A satisfy this characteristic equation, and with this we can say that the nth power of any n cross n matrix can be written as linear combination of its lower powers, that is in terms of I, a square and so on. In fact, basically it is what you can simply write this as simply lambda to power n plus some a n minus 1 lambda n minus 1 and so on, plus this a naught, you can write it as 0, and when a satisfy, then a to power n plus a n minus 1 a to power n minus 1 and so on, right, and a naught I equal to 0. Now, here we can write down the a n as linear combination of I, a square up to a n minus 1. So, that is the idea we can get from Cayley-Hamilton theorem, that a to power n can be written as linear combination of its lower powers. So, if a to power n can be written as a linear say lower powers of I, a square and a n minus 1, so is a n plus 1 can also be written as linear combination of I, a square and a n minus 1, and hence all the further powers of a may also be expressed as a linear combination of I, a square and a n minus 1, and in this way we can simply say that e to power a t can be written as a powers of the matrix into some say polynomial times powers of matrix A. So, I can write e to power a t as summation k equal to 0 to n minus 1 q k t into a to power k. Now, where q the coefficient q k t are scalar polynomial in t, and based on this method, this Poisson developed two useful methods to calculate e to power a t as a polynomial in A. But here we will take only one simpler one. If you want to discuss this, then I may refer a book by Tom Aberstall, and there you can get both the there we can have say more than two method to calculate this e to power at. So, I am just giving you one idea of this algorithm. So, in this method we are not calculating e to power at in direct powers of a to power k, but some function of matrix A. So, here this theorem 2 gives the Puzzle method to calculate e to power at. So, theorem goes like this, that let lambda 1, lambda 2 and lambda n be the eigenvalues of n cross n matrix A. Then we define a sequence of polynomials in A as follows: P naught A equal to I, Pk A is basically product of A minus lambda I, m is from 1 to k. So, it is not given directly in terms of A, but it is powers, lower powers of A is given. So, Pka is basically product of m equal to 1 to k, A minus lambda mi for k equal to 1 to n. Please observe here that P and A is basically what? Product of m equal to 1 to n, A minus lambda n I, sorry, lambda mi, and if you look at, this is basically product of what? Product of A minus lambda 1 I, A minus lambda 2 I, and so on. It is A minus lambda n I, and this is nothing but the value 0. So, P and A is having value 0, and for all others Pka is defined like this. Then we can write e to power at in terms of linear combination of these Pia as follows: e to power at is written as k equal to 0 to n minus 1 rk plus 1 t into Pka, where the coefficient rk plus 1 t can be obtained using recursive relation and of system of linear differential equation as follows, where r1 dash t equal to lambda 1 r1 t, r1 0 equal to 1, and r dash k plus 1 t equal to lambda k plus 1 rk plus 1 t plus rk t, where rk plus 1 0 equal to 0 for k equal to 1 to n minus 1. So, if you look at this these some system of linear differential equation of first order, and we can easily solve this system of linear these scalar valued linear differential equation of first order. So, after solving these coefficients in a recursive manner, we can, and having Pka, we can calculate e to power at. So, first let us prove this, and then we will see certain example based on this theorem. So, let us prove this. So, let R1 to Rn t be the scalar function given by 2, and define a matrix function f by the equation f t equal to k equal to 0 to n minus 1 r k plus 1 t Pka. That is what we here this we assume as some f t, and we want to show that e to power at is your f t, and here we use the existence and uniqueness theorem to show the equality. And here please observe that the value of f of 0 is r1 0 p naught a equal to I. If you look at here, it is what? F of 0 is basically summation k equal to 0 to n minus 1 r k plus 1 0 Pka. Now, if you look at what is the value of rk plus 1 0, then go back here, rk plus 1 0 is 0 for k equal to 1 onward. So, it means that r2 0 is 0, r3 0 is 0, and so on. So, only non-zero value is attained at r1. So, it means that when you put k equal to 0, then we have r1 0 and p 0 a. For all other values, we have value 0. The scalar coefficient r2 0, r3 0, these are all 0. So, r1 0 p 0 a is basically, r1 0 is basically 1, and p 0 a is defined as identity as we defined here. So, this means that f of 0 is identity and f t is given as this. So, here we want to prove that f t is equal to e to power a t by using existence and uniqueness result of the initial value problem x dash t equal to a x t comma x 0 equal to I. If you look at here, e to power a t satisfy this differential this initial value problem, because e to power at if you differentiate, then we will get a e to power at, and e to power at calculated at 0 is giving as I. So, if we can show that f t also satisfies this differential equation, that is f dash t equal to a f t, and f of 0, this we have already obtained, that it is f 0 equal to I. Then since this initial value problem must have only unique solution, so f t has to be ideally equal to e to power a t for all t in that interval I. So, that proves our result. So, only thing we have to show now is that f dash t equal to a f t. So, for that let us differentiate this expression given in 3 and see what we are getting. So, differentiating both the sides of equation number 3 and using the recursive relation 2, we have the following thing. So, f t is this, and if you differentiate this, what you will get, let me write it here, f dash t equal to summation k equal to 0 to n minus 1 r dash k plus 1 t p k a. So, this is independent of t. So, only thing you have to write down r dash k plus 1. So, so k equal to 0 means r 1 dash t. So, let me use here r dash k plus 1 t is equal to the following thing. So, let me write it here, and we can say that it is that lambda k plus 1 r k plus 1 t plus r k t, that is the expression for r dash k plus 1 t, and that is p k that we are just putting. So, now since here your summation start from k equal to 0 to n minus 1. So, when you put k equal to 0, we have r 0 t, and r 0 t we are defining it 0. Why? Because for k equal to 0, the expression is r dash t. So, r dash t is basically what? R 1 dash t is equal to lambda 1, let me write it here, r 1 dash t is basically, r 1 dash is lambda 1 r 1 t. So, it is lambda 1 r 1 t. So, it means that here your r naught is 0, we have assumed. So, r naught t is equal to 0, we are assuming, and we can write it this expression. So, now we simplify it a little bit further, and we write k equal to 0 to n minus 2, first term, the r k t into p k, and this summation is starting from k equal to 0 to n minus 1, but when you put k equal to 0, then the r naught t is 0. So, actual summation will start from 1. So, 1 means r 1 t onward. So, rather than writing k from 0 to n minus 1, we are writing as k from 0 to n minus 2, and we write r k plus 1 t into p k plus 1 a. So, here what we have done is this r k t and p k a, and here it is k equal to 0 to n minus 1. If you put, then this is nothing but k equal to 1 to n minus 1 r k t p k a, because corresponding to k equal to 0, your r 0 t is 0. So, now you simply replace, in place of k you can write it L plus 1. So, it means that I can write here that this implies that L will start from 0 to n minus 2, and this is R L plus 1 t p L plus 1 a. That is what we have written here, that k equal to 0 to n minus 2 r k plus 1 t into p k plus 1 a, and second term is as it is, that is k equal to 0 to n minus 1 lambda k plus 1 r k plus 1 t p k a. Now, we want to show that f dash t minus a f t is equal to 0. So, for that we can look at here, we have f dash t is equal to summation k equal to 0 to n minus 2 this r k plus 1 t, your p k plus 1 a, plus summation k equal to 0 to n minus 1, and what is here, it is lambda k plus 1 r k plus 1 t into p k. So, lambda k plus 1 r k plus 1 t into p k a. Now, look at f dash t minus a f t. What is f t here? So, let me write it here, k equal to 0 to n minus 2 r k plus 1 t pk plus 1a plus summation k equal to 0 to n minus 1 lambda k plus 1 rk plus 1 t pka minus a times ft. Ft is what? K equal to 0 to n minus 1. Let me write it. The expression say it is rk plus 1 t pka. So that we are writing here rk plus 1 t and pka. Right. Now let us calculate this value. So here I will write it in say summation k equal to 0 to n minus 2 rk plus 1 t pk plus 1 a plus k equal to 0 to n minus 1, and we can write it here lambda I minus a lambda k plus 1 I minus a rk plus 1 t into pk. Is it okay? So we can write it like this, and this we can write it k equal to 0 to n minus 2 rk plus 1 t pk plus 1 a. Now if you observe here that this rk plus 1 t is just a scalar quantity, I can take it out. So rk plus 1 t I am writing here k equal to 0 to n minus 1, and this is what lambda k plus 1 I minus a into pka. Now my claim is that this is nothing but minus pk plus 1 a. So how we can look at, if you look at the expression for this pka, so pk, now what is the value of pk plus 1a? So pk plus 1a is basically a minus lambda k plus 1 I into pka, right. So but here we have lambda k plus 1 I minus a into pka, so that I am writing as minus pk plus 1a. So that I am writing as minus pk plus 1a. So if we are writing this as a minus pk plus 1a, then I can write this as summation. So it is basically f dash t minus aft equal to summation k equal to 0 to n minus 2, and what is here rk plus 1 t pk plus 1a. So here rk plus 1 t rk plus 1 t pk plus 1a minus summation k equal to 0 to n minus 1, and what is here it is rk plus 1 t. So rk plus 1 t and pk plus 1a, right. So if you look at everything will be cancelled out, only say last term will be left, that is corresponding to k equal to n minus 1. So if you, because both are same up to n minus 2 here. So what is left here is minus r n t and p n a. Is it okay? Now yeah, it is t. Now what is p n a? So p n a, so this is p n a, and we have already calculated p n a as 0. So it means that this is nothing but 0. So it means that f dash t minus a f t is equal to 0, and we already know that f of 0 is equal to identity. So what we have shown here that f t satisfies this initial value problem, but e to power a t is already satisfying this equation, and we have done. So that is what we wanted to prove here. So here once we, here from this onward we have shown, and there is an alternative way to handle this situation. The alternative way is that you subtract lambda and f of t, and then we simplify this. That I am not going to do it, but we are just simply reaching up to this point that f t satisfies the differential equation f dash t equal to a f t and f 0 equal to I, and we already know that e to power a t is satisfying this, and by existence and uniqueness theorem we simply say that f t is equal to e to power a t for all time t. So that is the proof. So e to power a t can be written as the expression which we have already wanted to prove is this, that e to power a t is equal to summation k equal to 0 to n minus 1 rk plus 1 t into pka, where rk t is defined in a recursive manner using the relation given in 2. So, this proves the theorem 2, and we can use this result to find out e to power at for a given matrix. You may wonder that why we have discussed several methods to find out e to power at, then why this method is given to us. In fact, because of its nature, you can find out a computer program to calculate e to power at in a very easy manner. So, this algorithm, this may be treated as algorithm to calculate e to power at using your computer also. So, it may be little bit difficult when you use this algorithm to solve your e to power to find out e to power at using your pen and pencil, but it is quite useful when you write this as an algorithm. Anyway, so now example 2 is that express e to power at as a linear combination of I and A when A is a 2 cross 2 matrix with both of its eigenvalues equal to lambda. So, here the condition is that both of the eigenvalues is equal to lambda, then how we can find out e to power at. So, so first thing, since it means what is given here, that lambda 1 is equal to lambda 2 equal to lambda, and your scalar equations are given as r1 dash equal to lambda r1 t and r1 0 equal to 0, and r2 dash t equal to lambda r2 t plus r1 t r2 0 equal to 0, and we can easily solve this equation. R1 dash t is this is nothing but r1 t equal to lambda t. So, basically this is some constant time e to power lambda t, and that constant will be fixed by this initial condition, that is r1 0 equal to 1. So, r1 t is equal to e to power lambda t. Now, to find out r2 dash t, we have r2 dash t minus lambda r2 t equal to e to power lambda t, and we can simply say that if we multiply by e to power minus lambda t throughout, then I can write this as d by dt of r2 t e to power minus lambda t equal to 1, and then if we integrate, then r2 e to power minus lambda t is equal to t plus some constant c, and you can fix your constant by condition r2 0 equal to 0. So, it is 0 equal to 0 plus c. So, c is coming out to be 0. So, r2 e to power minus lambda t is equal to 0, or we can say that r2 t is given as t e to power lambda t. I am using one method, you can use any of the method which you know. So, here r1 t and r2 t is known to us now, and p naught a is given as I, and p1 a is nothing but a minus lambda I. So, now e to power at is written as this r1 p naught a, that is e to power lambda t into p naught. So, let me write it here, it is basically r1 p naught plus r2 p1 and so on. So, now we r1 is e to power lambda t, p naught is I, plus r2 is t e to power lambda t, and p1 is a minus lambda I, and we can write down the expression for e to power at as e to power lambda t, this 1 minus lambda t into I plus t e to power lambda t into a. So, so this is true for any matrix whose size is 2 by 2 and all the eigenvalues is equal to lambda. Is it okay? So, now so we have calculated e to power at in this case when A is 2 cross 2 matrix and both the eigenvalues are same and it is equal to some value, let us say lambda. Now, let us consider one more example. Here also we need to find out e to power at. Again the matrix is of size 2 cross 2, but the eigenvalues are distinct, that is lambda is not equal to. So, in this case let us first solve the system of linear differential equation r1 dash t equal to lambda r1 t and r1 0 equal to 1, and r2 dash t equal to mu r2 t plus r1 t, where r2 0 equal to 0. So, as we have pointed out, the r1 t is nothing but e to power lambda t, and if you want to solve the second equation, then it is what, r2 dash t minus mu r2 t equal to e to power lambda t. So, here if you multiply by e to power minus mu t, then what you will get here, we can get d by dt of r2 t into e to power minus mu t is equal to e to power lambda minus mu n t. So, this we can write it r2 t e to power minus mu t equal to e to power lambda minus mu t divided by lambda minus mu plus some constant. Now, r2 0 is 0. So, this is 0 and this is 1 upon lambda minus mu plus c. So, constant is given as the minus of lambda minus mu. So, so constant is this lambda minus mu, and you can put it here, then you will get this as so let me write it here, r2 t is basically multiply e to power mu t. So, here we are e to power lambda t divided by lambda minus mu plus e to power mu t divided by mu minus lambda. So, when you simplify, you will get this, that e to power lambda t minus e to power mu t divided by lambda minus mu. So, here we can get r2 t. So, now P naught is as it is I, and P1 is a minus lambda I. Then you can write e to power at as e to power lambda t I plus this r2 t, that is e to power lambda t minus e to power mu t upon lambda minus mu into P1a, that is a minus lambda I, and when you simplify, you will get this expression. So, this expression is will give you the expression for e to power at of for 2 cross 2 matrix, where both the eigenvalues are unequal, are not equal. So, with this I stop here discussion of finding the fundamental matrix e to power at for the autonomous case, and next lecture we will try to focus on non-autonomous case and try to see whether the similar kind of expression is available in the case of non-autonomous system or not. So, with this that is all, and we will continue in next lecture. Thank you very much for listening. Thank you.